Okay, so our next speaker is guiltygyoza from Topology. He'll be introducing RAM to the world computer. Please give him a big round of applause.
Hello everyone, I'm guiltygyoza. I also go by Thomas in the real world. I'm a co-founder of Topology, and today I'm glad to be here to propose a different kind of decentralized application or decentralized program that is different but complements smart contracts. So what we really care about at the end of the day is to build better world computers. And we recognize three properties that characterize what a good world computer should satisfy. So number one, it should operate on a credible neutral protocol stack, because if it doesn't operate on a credible neutral stack, we might as well use cloud computing. The second would be it needs to accommodate as many concurrent users as possible to be a world computer. By definition, users access the same computer from around the world concurrently, and so it should have massive concurrency. The third property will be it needs to provide an open world programming environment, because it should allow people to deploy programs where when programs crash or behave erratically, it should not crash the underlying system, and programs should be able to freely interact with one another with the highest possible interoperability. So we have blockchains, and the Ethereum blockchain is the pioneer of the world computer concept, right? So we can identify the commonality among blockchains. They all operate on some notion of Byzantine consensus, which allows nodes in a distributed system to reach agreement on the ordering of transactions or ordering of operations. And so we all know that Bitcoin uses CPU power to vote, and for Ethereum it uses your voting power is basically proportional to the number of states, capitalized states in the system. We want to point out that all blockchain basically operates in a single-threaded model, which means that transactions are included in order in a total ordering. Operations do not overlap, so you basically need one transaction to complete before you start the next transaction. So we are all concerned about the scaling problem of blockchain. The prevailing thesis for Ethereum scaling will be modularity, right? So the modular thesis basically says, okay, I have a thread that's very congested, so let us run a lot of application threads in parallel and let these threads settle their traces on the parent thread or the state space of the parent thread. The problem obviously is locking, because even if you move to the application thread, you still operate on a single-threaded model. So for an application that requires a lot of people to concurrently use it, you will still ask these users to lock one another out in order to have their transactions included in total order. And if you look at Ethereum's block time is about 12 seconds long. 99% is basic consensus, right? And so you have projects like Monad, for example, that tries to parallelize the execution. That basically accounts for less than 1% of the block time. You have the 99% of block time still dominated by basically people, basically these nodes, basically proposing and voting and trying to get their block being endorsed by the blockchain. Another complementary approach to scale blockchain will be to use ZK rollup, for example, like Starknet. And the idea is that instead of settling these traces optimistically, let's settle the traces that are sort of compressed in a mathematical way so that the underlying blockchain can verify these traces without trusting the application thread. And I think this approach basically sort of justifies that, okay, we can have sequencers that are centralized and we can have provers that are centralized, because math never lies, and the parent thread can always verify if bad things are being deposited. Well, the problem then is you basically introduce liveness bottleneck on the upper layer. So you introduce censorship, and you introduce liveness problems, and the blockchain stack is very complicated, and having prover involved and I think there are projects that are trying to make prover networks that essentially add to the complexity of the already very complex protocol stack. And finally, even if you move to a ZK rollup, you're still operating in a single-threaded model, so you're still running an application on a single thread. So we can look at the underlying consistency model and to see that, okay, maybe there's some underlying assumption that we can break free from. All blockchains operate on a consistency model called strict serializability, which means that number one, operations are put in a total ordering, common to all nodes, and second, operations do not overlap. So you do not allow parallelism. And there is a weaker model called causality or causal consistency model, which is actually the strongest possible model that allows you to do coordination-free execution. And coordination-free execution basically means that we do not need to use any consensus mechanism. As long as information are disseminated across the nodes, they can all reach consistency. That basically allows us to bypass the entire consensus process and the voting process of the typical blockchain. So the basic building block will be to use a hash graph, right? So the hash graph, the underlying system model is this. Imagine a distributed system comprising of many processes, and each process is a single thread. Furthermore, each process can generate events, whatever events, and these processes communicate by passing messages asynchronously. And these messages will carry as their payload the events. So process A will inform process B about the events generated locally, and process B will learn about that via synchronous message passing. So this is the basic sort of distributed system model. Okay, so we can construct a hash graph where these messages would report their causal dependency of messages that precede them. So if you look at this graph, the message C2 on the right reports causal dependency of A2 and B2, and so on and so forth. So these arrows are causal dependency reportings. And it doesn't just report the A2, it reports the hash of A2, which in turn report in itself the hash of B1 and so on and so forth. So you can realize that just looking at C2, it actually summarizes or contains the entire graph. Just like a blockchain, if you look at the block header of the highest block number, it basically summarizes the entire blockchain. If you change anything in the past, it changes the block header hash instantly. And, so we can talk about merging hash graph, because imagine a distributed system where all these processes are manipulating the same hash graph asynchronously and in parallel. So they will have different hash graphs, and if we don't merge them, it's not very interesting, because these replicas essentially are not synchronous and they're not in the same system. If you look at a hash graph, we can merge them. If two hash graphs start with the same state, we can always merge them into another hash graph that respects all causal relations encoded in the hash graphs. And we can merge these hash graphs via two mechanisms over the peer-to-peer network. One is the pole model, where these nodes sort of connect to other nodes and engage in a reconciliation or anti-entropy procedure, basically exchanging their graphs and trying to reconcile their graphs. So this is the pole model. And the push model will basically be gossiping, so standard way of transmitting information on a peer-to-peer network, the basic sort of academic algorithm. So, okay, so what's interesting about these is that if we can always merge two hash graphs into another hash graph that preserve all causality information, we basically say this hash graph program is invariant confluent. And invariant confluent is a property about a program that says, if I have a program that is invariant confluent, I can execute this program in a distributed manner without any voting or coordination. So this basically is the property that guarantees this consistency without having to do any consensus mechanism. Note that I-confluent program or invariant confluent program is not Turing-complete program. So this thing does not sort of overpower or replace blockchain. Blockchain is excellent at total ordering, non-overlapping operation. This is not Turing-complete program, but this is the strongest guarantee we can have without having to use any consensus. And another property about these invariant confluent program is it can be absolutely immune to cyber attacks. So blockchain basically deploys countermeasures to cyber attacks, right? By assuming, okay, for a Tendermint-like system, you would assume that you would have, let's say, 2f+1, you would have basically f Byzantine nodes at most in a network of 3f+1 nodes. For Ethereum, it's like assumption of if you have 33% of the network corrupted, then the network can be stalled, and if you have 66% of the network corrupted, then basically your finality can be reverted. So there's always some kind of assumptions and countermeasures to make cyber attack expensive, but not impossible. But for this kind of system, even if you have a network where 99% of the nodes are Byzantine, as long as the correct nodes still form a connected graph, they can talk to one another via one another, then these characters can operate correctly. And so with these properties, it will be interesting to ask, okay, so what can programmers build applications with it? One way to abstract these properties would be to use CRDT. So CRDT is conflict-free replicated data type. It's an abstract data type that basically abstracts all of the properties above. if you have CRDTs that give you data types such as the register, the atomic data types, and it gives you array and map and set and composable maps or recursive maps, which is JSON, then you will have, as a developer, you will have excellent expressivity about whatever behavior you want to program. These CRDTs are composable, and the sort of the connection between hashgraph and CRDT is that we can use hashgraph to transport operations that are happening through CRDT, or if we use the delta model, we can transport the deltas that are happening through the CRDTs. And if we use a hashgraph to transport CRDT, we can preserve all the properties above. So we're proposing a new kind of programs that are called live objects. So for a typical programmable blockchain, you will run smart contracts. Because these are not Turing complete, so we can't reuse the term smart contract. Instead, we propose live objects. So live objects is an object in the sense of object-oriented programming. It is stateful, it encapsulates state, and exposes method for manipulating and querying its state. And it's live because it provides you with very, very low response time, because you run a replica of the object locally and you transact against your own replica locally, so it basically gives you instant confirmation. If you look at a live object, it's also an actor. So we want this object to be able to interact not via synchronous function calls, but via asynchronous message passing. So that way we can have loose coupling among these objects. So a couple of sort of internal structure of the object will be, every object is an instance of a blueprint, which is your class. These blueprints are composable, so you can do class composition. Every object is stateful, obviously, and the state is typed by CRDTs or by other blueprints. Each object will have its interface, and this term sort of is coming from Smalltalk because we're very fond of the Smalltalk abstractions. Smalltalk is the mother of object-oriented programming. So interface basically specifies the set of signals that an object responds to. It has obviously signal handlers, which are functions that are being called upon when signal is derived. And finally, it needs to define two things. It needs to define a view function that materializes the state of the object, and it needs to define a merge function so that when I have two replicas of the same object, I can always merge them together. There are three key affordances for live object. One is transacting with live object is by default free, so there's no transaction cost because you're always running a local replica. You don't rely on any proof of resource, whether it's proof of CPU power or proof of stake of an external network. So you're not paying for other workers to provide utility for the correct operation of a live object. So transacting with an object is basically free. You can transact it against an object at local speed. So because you don't wait for consensus, transaction is instantly confirmed. So you can transact it as, say, 60 frames per second, which is sort of typical frame rate in modern video games. Finally, we would have loose coupling because these objects, when they interact with one another, they don't lock and switch context. They basically pass messages and they wait for messages to be returned asynchronously. So this will be a pseudocode for a live object that implements a social graph. And so, as we know, Farcaster is an open social graph application. If you look into its hub network basically is a server network that serves a set of CRDTs that represents this hash graph. Roughly 8 CRDTs that represent adding posts, removing posts, reactions, and people following other people, and so on and so forth. So we can implement a social graph or basically any kind of relationship graph as a live object. So this protocol basically allows you to add register new users with the object. It allows you to add posts and remove posts, and it allows you to react to posts. And this sort of code represents a multiplayer simulation. So the idea is that we can make a multiplayer simulation program with a live object, allowing people to concurrently interacting with each other in a simulation world. And the question will be, how do you implement collision, right? Because I think for people that are familiar with eventual consistency, you will ask, well, eventual consistency doesn't give you double spending attack protection, right? Because you can have a state variable that are being manipulated by concurrent processes, and if both of them subtract the same integer by 1, which starts with 1, then you get a -1. And if you have an invariant that said an integer should never go below 0, then your invariance is violated right there. And collisions sort of work in the same way, right? In a video game, you would say no two rigid bodies can ever overlap. So basically, you have a double spending problem, but sort of contextualized in the game context. Well, we can do collision handling in a different way by compensating. So we can say, okay, every rigid body has a repulsive field around itself, and when you're merging these replicas, you will basically check that these fields intersect, and you will push these players or rigid bodies apart from one another, thereby resolving their collisions. And the next slide will show you a prototype that we did last year, where click it. Yeah. So these are about 8 different users logging into the same CRDT program, and every user is represented by a penguin, as you can see. This is purely peer-to-peer, so there's no authoritative server determining the operations ordering, and there's no blockchain behind this. This is just operating peer-to-peer between browsers. And the next slide will be to implement collision, because as you can see, penguins can basically overlap among one another. So the next slide gives you another proof of concept where we have collision handle. And so these two penguins, one operated from Taipei, the other operated from, I think, east coast of the US. And as you can see, the collision is working, and the collision basically works by compensating each other. This prototype actually uses a very stupid way, which is we have inboxes for these players, and whenever they intersect, they will send a message to the other inbox saying, hey, you should back off. However, this approach is not BFT. And so the repulsive field approach, the compensation approach that I mentioned earlier, will give you convergence guarantee, and it will give you BFT. Okay, so with all these abstractions introduced, we can now talk about RAM. So random access memory is an interesting analogy that we want to introduce, because first of all, random access basically means that you can access specific data in your memory space with constant time. And in this context, you can subscribe to an individual live object disregarding other live object. And this is not possible with blockchain, where you basically have to synchronize the entire state of a blockchain that comprises the entire universe of smart contract programs, many of which you may not care or may not interact on, but you still have to synchronize the entire chain. But for a live object, you can basically subscribe to this message in a standard public subscribe, and you can synchronize just that object. So it gives you loose coupling, and it gives you the ability to run an object replica locally without having to do RPC and relying on centralized operators. The second analogy will be caching. So RAM typically works as caches to the CPU, and for live objects, because these replicas are operating locally, closely to where the compute happened, it almost works like a cache, but it's a network of caches, where every sort of node in the system is a user running a local machine. And in order to do that, it's important that we keep the memory footprint very low, right? So there is a high requirement to operate a blockchain node, as we know. I will be describing how we can keep memory footprint low later. And the third property will be ephemerality. So the idea is that when a live object has no user transacting upon it, it doesn't have to live in this sort of asynchronous network. We can snapshot it and put it on DFS. So we can basically eject it out of this network. When someone wants to use it, we can revive or rehydrate it from the IPFS and have people use it in terms of basically across replicas, the same object. And so these objects can be ephemeral, also sort of coinciding with the idea of RAM, having data that are cached and needs to maintain coherence with the main memory and so on and so forth. So we think this is a suitable analogy. And this slide shows that how my two objects interact with one another. So we want to have a synchronous message passing. So here you can see object XYZ, and object X passes the signal to object Y. The message X9 is the message that initiates the signal to object Y, which delivers the message Y5. And so you can see that how the pointers work. Y5 causal dependency is Y2, as well as X8, which is the dependency of the other object, the sender object. And similarly, for Y7 signaling Z, delivering the message Z5, Z5's dependency includes Z3 as well as Y4 and Y6, which is the dependency of the sender object. Because you want the receiver object to be able to verify the dependency of the sender object to basically minimize trust. So this will be similar to how when you're going across from blockchain to blockchain, you need the receiver chain to run a like line of the sender chain to basically verify the incoming message. Okay, so now we're ready to look into the intuition behind how we might build a protocol stack for this. So we have to start with snapshotting. So snapshot is the idea that, okay, I have all these replicas of the same object, and they may look very different, because every replica is operated by a process, and every process is transacting against it very fast. such as 60 hertz. And so you will have a replica that some part of it will be the same, but the rest of the replicas are different from process to process. Global snapshot basically means, okay, I have all these replicas of the same object. What is the state of the object exactly? You're asking a question that will require you to collect information from all the processes, and you will say, if I look at all the processes and in-flight messages, I can construct a global state at a given moment. And if you have an object that works in a permission model, or as in if you have processes that are leader processes, you can ask these leader processes to form standard global snapshot algorithms, such as the landing transport algorithm. But if you have objects that are operating in the open, where people can join and leave without permission, then you need to operate in a very different way. Global snapshot here will be practical. Imagine an object where people can log in and log off. And if you define a snapshot as, I need to collect information about this object from everyone accessing the object, even because people can log on and out, and because of the underlying network conditions of the P2P network, it is basically impractical to ask everyone. So then the question here is, okay, if I cannot ask everyone, so who do I ask to get a state of the global snapshot? This becomes a consensus problem, which means that on an open network, we need to agree upon what is the state of the replicated object that may have many, many different replicas. After a snapshot, we can talk about compaction. So compaction is the idea that because these live objects are being transacted upon so fast, they will grow very fast. So we cannot sort of afford to push state expiry as a problem to a very late of a blockchain. We have to tackle state expiry from the very beginning. Compaction basically means that if I have nodes that are stable, meaning that all future events will have arrived after these nodes, then I can compact the nodes before the stable node. So if you look at this graph, if you assume F and G are stable, we can compact A, B, C, D, E. So in this process, we compact A, B, C, D, E to the phi message, and we forward the state from S to S prime by evaluating the graph from A up to E. And this will allow us to keep the graph small. So imagine the scenario where the graph is growing very fast because you have a lot of people transacting against it at a very fast pace. And in order to not have unbounded memory problem, you have to also compact the graph very fast to catch up with the rate at which messages are being added to the graph. And the problem here will be, okay, what part of the graph can I safely compact? Because you will have objects that are operating across many different replicas. If you compact some portion of the graph that is not yet received by other replicas, then you might do something very unsafe. So the question again is the consensus problem, is how do we agree on a part of the graph that is safe to be compacted away and to be pruned away? And so basically we need some notion of consensus. But I want to remind us that we don't need consensus for ordering the transactions for these objects. We only need consensus to pace and to determine the snapshots that are safe to be compacted away. We can use a layered architecture to look at the certain protocol stack problem. On the right, you will see from the bottom, we have a P2P messaging layer. So this is the standard sort of assumption where every point in the network can safely transmit information to another point in the network. On top of this messaging layer, we construct a causal consistency layer, which is a hash graph abstraction that I talked about earlier. So you will have hash graphs that are reconciling with one another, and causal relations among events are preserved. On top of the causal consistency layer, we can build live objects. So this is your live objects that are operated for free. But then, if we need to introduce consensus and we need to prune away these graphs periodically, we can introduce a threshold witness layer on top. Threshold witness layer basically means that in a distributed system, an information has been witnessed by a threshold amount of nodes in the system. And furthermore, this information about witnessing is also being witnessed by a threshold amount of nodes in the system. And so you will have this sort of symmetric knowledge of what I know, what other people know in the distributed system. That's a threshold witness problem. On top of the threshold witness problem, we can do consensus. So if you're familiar with how Borchardt works and how the Tusk consensus work, this is basically the underlying model that they operate on, the DAG-based blockchains. Okay, so I also want to point out one thing, which is you can use live object protocols outside of this, outside of the consensus. Similar to how the World Wide Web, you can basically take HTTP protocol and you can basically operate a closed network that's separate from the World Wide Web. So this is a free protocol. It's an open source licensed free protocol. But if you want to have rich interoperability and like these sort of timing and racing conditions resolved for you, then it's useful for your live objects to opt into this layer of witnessing and consensus network. Okay, so this shows a little bit intuition of how a threshold merge hash graph can work. So on the left, you have a message that's being broadcast to the network. And people are acknowledging or acting this message, and you basically aggregate these as acknowledgement. But I also want to ensure that these acknowledgements are being witnessed by also sort of enough amount of people in the network so that everyone knows what everyone else knows. You have a knowledge symmetry problem. So I am broadcasting these acknowledgements in the network again, and I'm requiring people to acknowledge my acknowledgement back. So I'm counting how much messages are being acknowledged. You can define the threshold as a 2/3. So I can say, out of 3f plus 1 nodes in the network, I require a witness threshold of 2f plus 1, which is 66%. You can also say, instead of just operating on a node count, I can operate on stake. I can say, threshold witness is equivalent to 66% of the total capital stake in the network, in a proof of stake system. And if you have this, you can have information being recognized by the distributed system, and you can move forward with such information. For hash graph, that information will be exactly what part of the graph can we safely agree upon and compact it away, which gives you the periodic compaction and keep the memory bounded. One problem obviously is if you just look at the graph, you will see the communication complexity is O to N cubed, which can be very problematic. One standard way to reduce the complexity down to O N squared is to use some kind of leadership group or sortition, where you elect a group of leaders that are responsible for performing the threshold witness procedure, and every now and then you basically re-elect leaders via some leadership rotation algorithm. Okay, so once we have this mechanism, we can compact away the graph periodically. So if you look at this diagram, on the left you will have some portion of the graph that are being agreed upon, the graph that are being boxed in a dotted line. Compaction basically is taking in some state, evaluate the graph, and transition the state to a new state. But we want to keep the graph trust minimized, so we also want to prove the operation. So this is where we introduce the recursive scenario, which is how the MENA blockchain works by keeping itself very light. Right? So every state transition, I also need to recursively prove that my state transition is correct. So in this case, we will basically verify the previous proof and then prove the verification of the proof along with the latest compaction, so that every compaction is trust minimized and verifiable just by looking at the latest proof. So this is the mechanism that allows a graph to be succinct and small footprint. Therefore, the local node can always operate without having to delegate out the responsibility to another node and always rely on centralized RPCs to interact. Okay, so the status of the project will be paper draft V7.3 is up in GitHub. That is the QR code for the paper. And on the engineering side, we're performing a vertical prototyping effort. We want to be able to deliver non-PFP version of these objects to developers around the world by this summer so that people can poke at it. Because it is a different kind of programming paradigm that requires you to define merge operations. And so it's different from smart contracts, and we think it takes some time for people to, most people that are probably not yet familiar with CRDPs, to catch up to the thinking behind the CRDPs. On the research side, there are a lot of open items to work on. There is the compaction protocol that we need to work on. There is the protocol for these objects to write back to any blockchain, and it can be problematic, right? Because these objects operate in a synchronous manner, but blockchain is synchronous, and transactions are irreversible on the blockchain. So there is some security problems that need to be solved for these objects to transact against the blockchain. And the underlying broadcast algorithm needs to be improved upon, because how fast you broadcast information on the PFP network determines how fast these also information can be recorded in the object like that. And finally, because CRDPs are a relatively new programming paradigm, and this is a sort of new design pattern that needs to be figured out. So design patterns exploration is needed, and we foresee a lot of developer libraries that need to be built for people to define and develop their live objects composably. And finally, we're setting up an office in Berlin, in the Kreuzberg area, so it is basically close to the protocol team of Ethereum and Interchain Foundation and so on. So we look forward to work with protocol devs and engineers and researchers that are interested in consensus protocols and beyond. And just for the inquisitive minds, here's a list of open problems that we're working on. The first problem will be a consensus protocol that needs to minimize its complexity in communication. It's basically the amount of messages that are being sent across the network to basically pace the time, logical time from T+1. We need to maximize decentralization, but we also want to minimize the possibility of stalling. We need to ensure fairness, which in this context basically means that if a correct actor submits a message, the message needs to be included in the system with probability 1, instead of having any probability of being rejected. We need to keep the object very succinct. For those of you who may be familiar with how CRDP works, one thing about CRDPs being impractical in 2010s is because these graphs, the metadata of the graph grow very fast, and so you would have applications slow down after some time. So being able to safely prune these graphs is crucial to keep the memory footprint small and for every user to locally host these objects. And finally, we need to iterate on the proof-of-stake mechanism to ensure the nothingness state problem to be solved. The second problem will be crypto economics. Imagine if users are transacting with a live object at 60 times a second, but they have to cite transactions every time. That would just be impractical. So basically, we need a way for users to be able to transact with these objects without having to pay per transaction. And that requires different kind of crypto economics to basically charge user for the services that these consensus nodes are providing. We need to work on the broadcast algorithm that minimizes the number of round trips these messages are being sent to reconcile the graph. So the standard way to do this will be two replicas initiate a connection, probably over TCP, and then they send over their head for the graph. And when something is not matched, they will exchange messages back and forth until they reconcile the graph, right? But you'll see there's a lot of message round trip, and it is very inefficient. So there are other ways to improve this algorithm to allow faster information dissemination and graph reconciliation across the peer network. And also we want this object to reside in a global namespace so that these objects can always recognize one another, similar to how websites are recognized always by a universal resource locator or identifier on the web. Also, we need a lot more design patterns for live objects because traditionally CRDPs in the past 20 years have been basically used for collaborative document editing. So there's a lot of design pattern for how do you do rich markdown text and how do you collaborate on rich text objects, for example. But we are extending the use of CRDPs basically to all kinds of decentralized programs. So we need a lot of people working on different design patterns and so on. Just like how token standards were being created for blockchains so people can create safe tokens quickly. And so we're looking for researchers and engineers with skills in Go and Rust programming, low-level system programming. We're looking for people with skills in PV networking, cryptography, distributed systems, and interest in crypto economics. For those interested, you can email me or DM me on Twitter or Broadcaster. Thank you.
So just now you mentioned about the it sort of reminded me about the cloud blockchain too. So function is included because they also have async and message passing, and I think it really reminded me of that student. So maybe also depend on top of that programming languages to say that. The Tom project. You know the Telegram?
Oh yes.
I think they have a similar IP model.
Curious how to describe how this relate to Starknet as a peaceful ecosystem.
Yeah, so I think, first of all, we think live objects should be agnostic to any particular blockchain, so we should be able to interact with any blockchain. But strategy-wise, there may be an order at which we sort of allow these objects to interact with blockchains. Just like if you look at Farcaster, it basically worked from optimism layer 2 and start to be able to verify Solana signature so we can interact with Solana. So that is the first aspect. And the second aspect is we are pruning these graphs and performing recursive validity proof on it. So we need some recursive proof system, and Chiral VN might be one suitable VN for doing that.
One more question. It's not related to the last one. Since from my understanding that when communicating such network, for first time communicators that want to get the initial state of the light track, you have to basically look through the entire network to get the initial state. So say determine the initial state is accepted by the consensus. So since data get written so quickly onto the network due to the fact that it's in light track, how do you ensure a certain amount of consistency in the sense that as in, if A and B reads the graph at the same time, depending on model factors, it might read different states at a certain snapshot or certain time frame. Yeah. So what's the solution for this?
So I think we're talking about a catching up problem, which is when a new node joins the system and want to bootstrap, let's say, object X. The node needs to know which other nodes contain information about object X, and to be able to receive the graph from the object X. And if you just receive the heads of the object, it already allows you to verify because the heads contain the entire graph. But still, you need to, and the heads will allow you to add new events because new events will have causal dependence on the recent head. So just getting the heads will allow you to begin transacting with the object. But for an application that wants to render the state of the object, you need to get the state, not just the heads, because the state is what you would basically view the application in a view model. So I think you would, in a public subscribe model, you would have topic that maps to object IDs, and by subscribing to certain topics, you can begin to receive messages of that object ID. That basically allows you to start synchronizing with other replicas of the same object. And I think the detailed mechanisms is still being figured out, but there should be ways for a node to know which other nodes on a network has the state and to be able to ask for the state. That is the sort of the caching out problem. Once you're caught up with the rest of the nodes, you can start transacting against it, and then the entire sort of synchronization machinery kicks in.
Thank you.
Yeah, if there's no more question, we're looking for contributors, and if you live in Europe or if you like to live in Berlin or you're currently living in Berlin, welcome. Contact me and we can find a way to collaborate.